13.10 Wrap-Up. In this chapter we discussed polymorphism, which enables us to program in the general rather than program in the specific, and we showed how this makes programs more extensible. We began with an example of how polymorphism would allow a screen manager to display several space objects. We then demonstrated how base class and derived class pointers can be aimed at base class and derived class objects. We said that aiming base class pointers at base class objects is natural, as is aiming derived class pointers at derived class objects. Aiming base class pointers at derived class objects is also natural because a derived class object is an object of its base class. You learned why aiming derived class pointers at base class objects is dangerous and why the compiler disallows such assignments. We introduced virtual functions, which enable the proper functions to be called when objects at various levels of an inheritance hierarchy are referenced, at execution time, via base class pointers or references. This is known as dynamic or late binding. We then discussed pure virtual functions and abstract classes, classes with one or more pure virtual functions. You learned that abstract classes cannot be used to instantiate objects, while concrete classes can. We then demonstrated using abstract classes in an inheritance hierarchy. You learned how polymorphism works under the hood with tables that are created by the compiler. We used runtime type information, RTTI, and dynamic casting to determine the type of an object at execution time and act on that object accordingly. The chapter concluded with a discussion of virtual destructors and how they ensure that all appropriate destructors in an inheritance hierarchy run on a derived class object when that object is deleted via a base class pointer or reference. In the next chapter, we discuss templates, a sophisticated feature of C++ that enables you to define a family of related classes or functions with a single code segment. Summary. Section 13.1 Introduction. Polymorphism, page 535, enables us to program in the general rather than program in the specific. Polymorphism enables us to write programs that process objects of classes that are part of the same class hierarchy as if they were all objects of the hierarchy's base class. With polymorphism, we can design and implement systems that are easily extensible. New classes can be added with little or no modification to the general portions of the program. The only parts of a program that must be altered to accommodate new classes are those that require direct knowledge of the new classes that you add to the hierarchy. Section 13.2 Introduction to Polymorphism, Polymorphic Video Game. With polymorphism, one function can cause different actions to occur, depending on the type of the object on which the function is invoked. This makes it possible to design and implement more extensive systems. Programs can be written to process objects of types that may not exist when the program is under development. Section 13.3 Relationships among objects in an inheritance hierarchy. C++ enables polymorphism, the ability for objects of different classes related by inheritance to respond differently to the same member function call. Polymorphism is implemented via virtual functions, page 543, and dynamic binding, page 544. When a base class pointer or reference is used to call a virtual function, C++ choose the correct overridden function in the appropriate derived class associated with the object. If a virtual function is called by referencing a specific object by name and using the .member selection operator, the reference is resolved at compile time. This is called static binding, page 544. The virtual function that is called is the one defined for the class of that particular object. Derived classes can provide their own implementations of a base class virtual function if necessary, but if they do not, the base class's implementation is used. Section 13.4 Type fields and switch statements. Polymorphic programming with virtual functions can eliminate the need for switch logic. You can use the virtual function mechanism to perform the equivalent logic automatically, thus avoiding the kinds of errors typically associated with switch logic. Section 13.5 Abstract classes and pure virtual functions. Abstract classes, page 550, are typically used as base classes, so we refer to them as abstract base classes, page 550. No objects of an abstract class may be instantiated. Classes from which objects can be instantiated are concrete classes, page 550. You create an abstract class by declaring one or more pure virtual functions, page 551, with pure specifiers equals 0 in their declarations. If a class is derived from a class with a pure virtual function and that derived class does not supply a definition for that pure virtual function, then that virtual function remains pure in the derived class. Consequently, the derived class is also an abstract class. Although we cannot instantiate objects of abstract base classes, we can declare pointers and references to objects of abstract base classes. Such pointers and references can be used to enable polymorphic manipulations of derived class objects instantiated from concrete derived classes. Section 13.7, Optional, Polymorphism, Virtual Functions and Dynamic Binding under the hood. Dynamic binding requires that at runtime, the call to a virtual member function be routed to the virtual function version appropriate for the class. A virtual function table called the table, page 567, is implemented as an array containing function pointers. Each class with virtual functions has a table. For each virtual function in the class, the table has an entry containing a function pointer to the version of the virtual function to use for an object of that class. The virtual function to use for a particular class could be the function defined in that class, or it could be a function inherited either directly or indirectly from a base class higher in the hierarchy. When a base class provides a virtual member function, the derived class can override the virtual function, but they do not have to override it. Each object of a class with virtual functions contains a pointer to the table for that class. When a function call is made from a base class pointer to a derived class object, the appropriate function pointer in the table is obtained and dereferenced to complete the call at execution time. Any class that has one or more zero pointers in its table is an abstract class. Classes without any zero table pointers are concrete classes. New kinds of classes are regularly added to systems and accommodated by dynamic binding. Section 13.8 Case Study, Payroll System using Polymorphism and Runtime Type Information with Downcasting, Dynamic_Cast, Typeid, and Type_Info. Operator Dynamic_Cast, page 571, checks the type of the object to which a pointer points, then determines whether the type has an is-a relationship with the type to which the pointer is being converted. If so, Dynamic_Cast returns the object's address. If not, Dynamic_Cast returns 0. Operator Typeid, page 573, returns a reference to a Type_Info object, page 573, that contains information about the operand's type, including the type name. To use Typeid, the program must include header, page 573. When invoked, Type_Info member function name, page 573, returns a pointer-based string that contains the name of the type that the Type_Info object represents. Operators Dynamic_Cast and Typeid are part of C++'s Runtime Type Information, RTTI, p.571 feature, which allows a program to determine an object's type at runtime. Section 13.9 Virtual Destructors. Declare the base class destructor virtual, page 574, if the class contains virtual functions. This makes all derived class destructors virtual, even though they do not have the same name as the base class destructor. If an object in the hierarchy is destroyed explicitly by applying the delete operator to a base class pointer to a derived class object, the destructor for the appropriate class is called. After a derived class destructor runs, the destructors for all of that class's base classes run all the way up the hierarchy.